In unit number 3 we have studied partial differentiation. Now unit number 4 is applications of partial differentiation, in which we are supposed to learn Jacobians, functional dependence, maxima and minima for a function of two variables and later of three variables, errors and approximations. In this session let us discuss on functional dependence properties. If u, v are functions of x and y, then u and v are said to be functionally dependent if and only if Jacobian of u and v with respect to x and y is equal to 0. U, v and w, which are functions of x, y and z, are said to be functionally dependent if and only if the Jacobian of u, v and w with respect to x, y and z is equal to 0. And one more. If u and v are two dependent variables and x, y, z are three independent variables, then u and v are said to be functionally dependent if and only if these three Jacobians of order 2 by 2 must be equal to 0. We'll discuss some problems. Verify whether the following functions u equal to x minus y upon x plus y, v equal to x plus y upon x are functionally dependent, and if so, find the relation between them. So these are u and v. So we cannot get straight away the first order partial derivatives of u and v, so we'll first compute those and then find the Jacobian. Derivative of u partially with respect to x, here both numerator and denominator involves x, so we have to make use of quotient rule. In denominator x plus y square, in numerator x plus y into derivative of x minus y partially with respect to x, that is 1, minus x minus y into derivative of x plus y with respect to x partially, that is 1. After simplifying, it is 2y upon x plus y to the power 2. Derivative of u partially with respect to y, again u and y is in numerator and denominator both, so quotient rule. In denominator x plus y to the power 2, in numerator x plus y into derivative of x minus y partially with respect to y, that is minus 1, minus x minus y into derivative of x plus y partially with respect to y, that is 1, and we are getting that equal to minus 2x upon x plus y to the power 2. Derivative of u partially with respect to x, 1 upon x square, and then x into derivative of x plus y partially with respect to x, that is 1, minus x plus y into derivative of x partially with respect to x, that is 1, and that is equal to minus y upon x square. Finally, derivative of p partially with respect to y is in numerator only, so 1 upon x is constant, and derivative of x plus y partially with respect to y is equal to 1. This is the definition of Jacobian of u and v with respect to x and y. So w by w x, w by w y, w by w x, w by w y. Putting these expressions and simplifying, we are getting value of the determinant equal to 0. So u and v are functionally dependent. Let us identify the relation now. We see x plus y in first denominator and in the second numerator. So let us multiply so that it will get cancelled. U into v equal to x minus y upon x, and that is equal to 1 minus y by x. From the second relation we see that v equal to 1 minus y by x, that is y by x is equal to v minus 1. So after putting and simplifying, we are getting the relation u into v equal to 2 minus v. So when we say that two or three functions u, v or u, v and w are functionally dependent, that means it is quite possible to identify one more relation which involve only dependent variables, and we are able to eliminate all the independent variables. Next problem. Verify whether the following functions u equal to x minus y upon 1 plus xy, v equal to tan inverse of x minus tan inverse of y are functionally dependent, and if so, find the relation between them. So Jacobian finding, before that let us again find first order partial derivatives. Derivative of u partially with respect to x, again x is in numerator denominator both, and every time we are going to make use of this quotient rule. In denominator 1 plus xy bracket to the power to in numerator 1 plus xy into derivative of x minus y partially with respect to that is 1 minus x minus y into derivative of 1 plus xy partially with respect to x and that is y, and this is equal to 1 plus xy minus xy plus y square, that is 1 plus y square upon 1 plus xy bracket to the power 2. Similarly, partial derivative of u with respect to y in denominator 1 plus xy bracket square in numerator 1 plus xy into derivative of x minus y partially with respect to y, that is minus 1 minus x minus y into derivative of 1 plus xy partially with respect to y, that is x, and that is equal to minus 1 times 1 plus x square upon 1 plus xy bracket to the power 2. Rest two are easier. Derivative of u partially with respect to x is 1 upon 1 plus x square, and derivative of u partially with respect to y is minus 1 upon 1 plus y square. Now, the Jacobian of u and v with respect to x and y. After putting these expressions, we are getting again equal to 0. So, u and v are functionally dependent. Let us find the relation u and v. In v, there is tan inverse of x minus tan inverse of y. So, that is equal to tan inverse of x minus y upon 1 plus xy. And that is tan inverse of u. So, v equal to tan inverse of u or u equal to tan of v. This is the relation between the two dependent variables. Third problem. Verify whether the following functions u equal to sin inverse of x plus sin inverse of y and v equal to x square root of 1 minus y square plus y times square root of 1 minus x square are functionally dependent, and if so, find the relation between them. Again, we will be finding first order partial derivatives. So these two are easy. Derivative of u partially with respect to x is 1 upon square root of 1 minus x square. Similarly, w by y equal to 1 upon square root of 1 minus y square. Again, v by x is equal to, here differentiating v partially with respect to x, we are getting square root of 1 minus y square plus y times 1 upon 2 square root of 1 minus x square into minus 2x, and that is coming as square root of 1 minus y square minus x into y upon square root of 1 minus x square. We see that in v, role of x and y is the same. If we interchange x and y, then we will be getting v equal to y square root of 1 minus x square plus x times square root of 1 minus y square. So we can write del v by del y directly by making use of del v by del x. Here replace x by y and y by x. So that is getting as square root of 1 minus x square minus y into x upon square root of 1 minus y square. Jacobian of u and v with respect to x and y. Again, after simplifying, we are getting this is equal to 0. So u and v are functionally dependent. Let us find the relation. Here we see that in u there are sin inverse terms. So we'll be saying sin u. Sin u equal to sin inverse of x plus sin inverse of y. Let us use the formula sin of a plus b is equal to sin a into cos b plus cos a into sin b. Therefore, sin of u equal to x into, we know cos theta equal to square root of 1 minus sin square theta, and plus again the same thing plus square root of 1 minus sin square theta into sin of sin inverse of y is y, and this is x square root of 1 minus y square plus y square root of 1 minus x square. So the relation is sin u equal to v. Again, easy problem. Here we are going to have 3 dependent and 3 independent variables. Verify whether the following functions u equal to x plus y plus z, v equal to x square plus y square plus z square, and w equal to xy plus yz plus zx are functionally dependent, and if so, find the relation among them. So these are u, v and w. Let us find the Jacobian straight away. These are simple, so directly. So first row, derivative of u partially with respect to x, y and z, and that is 1, 1, 1. In the second row, derivative of v partially with respect to x, y and z, that will be 2x, 2y, 2z. And in the third row, derivative of w partially with respect to x, y and z, and that is y plus z, z plus x and x plus y. So instead of solving this directly, if we are making use of the properties of determinants, then things are becoming easier. So we see that in the second row 2 is common, we are taking it outside, and twice determinant of the remaining thing. Again, we see that x, y, z, let us add the elements in the second row into the corresponding elements of the third row, and that will be only third row will be changing that, and every element in the third row will be x plus y plus z. In the next step, we are taking away x plus y plus z outside, 2 into x plus y plus z, and 1 1 1 x y z 1 1 1. And we know that if any two rows or columns of a determinant are identical, then value of the determinant is 0. So here third and first are identical, so value of determinant is 0, and Jacobian of u, v, w with respect to x, y, and z is equal to 0. So u, v, and w are functionally dependent. So finding a relation in this case is also very easy. As you see, the terms in u, v, w state of a squaring u, that is ax plus y plus z square is equal to x square plus y square plus z square plus 2 times xy plus 2 times yz plus 2 times zx. The first three terms are equal to v, and the last three terms are equal to twice of w. So u square is equal to v plus twice w. This is the relation. Next problem. Verify whether the following functions u equal to y plus z, v equal to x plus 2z square, and w equal to x minus 4yz minus 2y square are functionally dependent. And if so, find the relation among them. So we have rewritten u, v, and w. Again, writing directly the partial derivatives is not a problem. So Jacobian of u, v, and w with respect to x, y, and z like this. So in the first row, derivative of u partially with respect to x, y, and z. So 0, 1, 1. In second, derivative of v partially with respect to x, y, and z will be equal to 1, then 0, and 4z. And in the third row, the derivative of w partially with respect to x, y, and z, that is 1 minus 4z minus 4y and minus 4y. Again, towards simplifying this determinant, we see we are trying to bring 0 here by making use of this one, and for that the necessary operation is c2 minus c3. So there will be no change in column 1 and column 3, and only column 2 will be changing. 1 minus 1 is 0, then 0 minus 4z is minus 4z, and this expression minus this expression will be equal to minus 4z. Minus 4z here. Let us expand now through the elements in the first row. So 0 0, and after that we are going to take care of this minus 1 to the power first row and third column, minus 1 to the power 1 plus 3 into this element 1 into minor of the element, drop all the element in the row, in the first row and the third column. We are getting this 2 by 2 determinant. We see first and second rows are the same, so value of determinant must be 0, and thus Jacobian of u, v, w with respect to x, y, and z is equal to 0. So u, v, and w are functionally dependent. Let us find the relation. So it is not so easy, but we see that there are square terms in v and w, whereas there are no square terms in u. So let us try to square u. That is y plus z whole square is y square plus z square plus 2yz. Further, we see here coefficient of z square is 2, coefficient of yz here is 4. So let us multiply throughout by 2. 2u square equal to 2y square plus 2z square plus 4yz. Further, 4yz, 2y square have negative signs. So let us take this to the left hand side. So 2u square minus 4yz minus 2y square, and that is equal to 2z square. Now let us concentrate. V equal to x plus 2z square. So if we are adding at right hand side x, so we'll have to add at left hand side also. So 2u square plus x minus 4yz minus 2y square equal to x plus 2z square, and thus 2u square, and these remaining three terms are nothing but w, and right hand side is just nothing but v. So we are getting quite easily the relation among u, v and w as 2u square plus w is equal to v. Another variety here. Verify whether the following functions u x minus y upon x plus z, v equal to x plus z upon y plus z are functionally dependent, and if so, find the relation between them. Till now we have seen two dependent, two independent variables, then three dependent, three independent variables. But here we are observing that u and v are only two dependent variables, whereas x, y and z are three independent variables. So we'll have to find out Jacobians which corresponds to order 2 by 2, and as such three Jacobians are possible. For that, let us simplify first the necessary first order partial derivatives. Del by u by del by x. Again, x is in both in numerator and denominator, so quotient rule. In denominator x plus z square, in numerator x plus z into derivative of x minus y partially with respect to x is 1 minus x minus y into derivative of x plus z partially with respect to x, that is 1, and x plus z minus x plus y, that is y plus z upon x plus z square. Similarly, del by u by del by y. Here we see that denominator is free from y, it is a constant, 1 upon x plus z is constant, derivative of x minus y partially with respect to y is minus 1. Del by u by del by z. Here z is in denominator only, so x minus y is constant, and derivative of 1 upon x plus z partially with respect to z is minus 1 upon x plus z to the power 2. Del by v by del by x. X is in numerator only, 1 upon y plus z is constant, derivative of x plus z partially with respect to x is 1, derivative of v partially with respect to y is in denominator only, x plus z is constant, so in bracket x plus z, derivative of 1 upon y plus z partially with respect to y is minus 1 upon y plus z to the power 2. And finally derivative of v partially with respect to z. Z is in both numerator and denominator, so again quotient rule, 1 upon y plus z to the power 2, that will be multiplied by y plus z into derivative of x plus z partially with respect to z, that is 1, minus x plus z into derivative of y plus z partially with respect to z, and that is equal to 1. So y plus z minus x minus z, z cancels, and that is y minus x upon y plus z to the power 2. So we have done all the hard work. Now we'll be finding the Jacobians one after the another. So here for Jacobian of u and v with respect to x and y, these are the elements we are writing these expressions, and the first is equal to 0. Similarly, the second Jacobian of u and v with respect to x and z, these are the elements, that is also equal to 0, and one more Jacobian of u and v with respect to y and z, that is also equal to 0. Thus all the three Jacobians are 0, so we can say that the two dependent variables u and v are functionally dependent. Now we have to find the relation between these two. Here we see in u denominator is x plus z, whereas in v numerator is x plus z. So let us take advantage of this. Let us bring both in the denominator. So u plus 1 upon v, that is x minus y upon x plus z, plus y plus z upon x plus z. In denominator x plus z, y cancels, x plus z upon x plus z, that is equal to 1. So u plus 1 upon v is equal to 1. This is the relation, quite easily done. Next problem. Verify whether the following functions u equal to sin x plus sin y and v equal to sin of x plus y are functionally dependent, and if so, find the relation between them. So these are the two functions defined. Straight away we will be finding the Jacobian of u and v with respect to x and y. So derivative of u partially with respect to x and y is cos x and cos y respectively. Similarly, derivative of v partially with respect to x and y, cos of x plus y, cos of x plus y. We see that this determinant is not equal to 0. So u and v are not functionally dependent. That means that it is never possible to eliminate x and y both and obtain one more relation which involves only u and v. And this is the last problem in this session. Verify whether the following functions u equal to x upon y minus z, v equal to y upon z minus x, and w equal to z upon x minus y are functionally dependent, and if so, find the relation among them. So we have written this. It will be easier to take the partial derivatives if we are taking the logarithm. So taking log of u equal to log of x minus log of y minus z. Likewise, we take log of v and w also. And let us see here Jacobian of u vw with respect to x, y, and z. That is, these are the first order partial derivatives, and from this we have to obtain the value of the determinant w by x. For that, differentiate this equation partially with respect to x. That will be 1 upon u w by x is equal to 1 upon x. That means w by x equal to u upon x. Then w by y, differentiate this partially with respect to y. 1 upon u w by y is equal to minus 1 upon y minus z, and therefore w by y equal to minus u upon y minus z. W by z, for this will differentiate the first relation partially with respect to z, that is 1 upon u into w by z is equal to minus 1 upon y minus z into minus 1, and thus w by z will be is equal to u upon y minus z. Similarly, we can find out the next 6 first order partial derivatives which have been written here. Now, for easiness, from first row u is taken outside, from second v, and from third w, and this is the remaining part. Again, in the next step, 1 upon y minus z from first row, 1 upon z minus x from the second, and 1 upon x minus y from the third row is taken outside, and this is the remaining part. After simplification, value of this determinant is coming as equal to 0, and the Jacobian is 0. So u, v, and w are functionally dependent. Finding the relation is not so easy here, and for that, see u plus v. We are simplifying u plus v, we are getting equal to this. Similarly, once we have written, we can directly write v plus w and w plus u. So the product u plus v into v plus w into w plus u is coming as this expression. Let us call this as equation number 1. I will find 1 minus u. 1 minus u equal to y minus z minus x upon y minus z. Similarly, we can find 1 minus v, 1 minus w, and let us take the product. And the product written in equation number 2. We see that equation 1 and equation 2 we have right hand sides the same, and hence the left hand sides must also be the same, and thus the relation among u, v, and w is u plus v into v plus w into w plus u is equal to 1 minus u into 1 minus v into 1 minus w. And thus in this session we have discussed sufficient number of problems on functional dependence. So make lot of practice, and in the next session we'll be coming with remaining applications of the partial differentiation. Have a nice day.